This video will be introducing sequences. A sequence is simply a list of numbers. So for example, 2, 4, 6, 8, 10, and so on is a sequence. The notation a sub n represents the nth term or the general term of the sequence. We call it the general term because we're not stating which term in the sequence it is. We're just being generic and saying, well, one of them in the middle, a sub n. The entire sequence is represented by a sub n being in set brackets. We know that a set is simply a list of numbers or objects, so it kind of makes sense that we're going to take all of these terms and put them in set brackets, and that'll give us a sequence. An infinite sequence is a function whose domain is the set of positive integers. The function values or terms of the sequence are represented by a sub 1, a sub 2, a sub 3, and so on. You'll notice that a sub n is kind of in the middle of the list somewhere. And our ... dots tells us that this goes on forever. A sequence whose domain consists of only the first n positive integers is called a finite sequence. So an infinite sequence goes on forever, while a finite sequence only has so many numbers. Please note that sequences are usually named with the letter A, but any lowercase letter can be used. Let's practice finding the first 4 terms of the 2 sequences listed here. We'll start with a sub n is equal to 4n minus 1. Now, a sub 1, notice that I have a 1 in the place where the n would be on the left side over here. So all we're going to do is replace the n on the right side with 1 as well, clean it up with our order of operations, and that'll give us the first term. So a sub 1 is 4 times 1 minus 1. A sub 1 is equal to 3. And we'll do this for all of them. So then a sub 2, that's going to be 4 times 2 minus 1, which is 7. A sub 3, 4 times 3 minus 1, 11. And lastly, a sub 4, that'll be 4 times 4 minus 1, which is 15. So here are our first 4 terms. Let's try another one. B sub n is defined to be negative 1 to the nth times n squared. Again, we're just going to be replacing the n on the right side with whatever the n is on the left side. So b sub 1, that's going to be negative 1 to the first times 1 squared. So 1 squared is 1. Negative 1 to the first is negative 1. This gives us negative 1. B sub 2, that'll be negative 1 squared times 2 squared. Negative 1 squared is positive 1. 2 squared is 4. Positive times a positive, we're going to get positive 4. B sub 3, that'll be negative 1 to the third times 3 squared. Negative 1 to the third is negative 1 times 3 squared, which is 9. That'll give us negative 9. And b sub 4, that'll be negative 1 to the fourth times 4 squared. So negative 1 to the fourth, that'll be positive 1 times 4 squared, which is 16. Positive and a positive, positive 16. And here are our first 4 terms of our sequence. You'll notice in this example, each term from one to the next alternates between positive and negative. You'll see that a lot with sequences, that you'll see this negative 1 to the n power. And that's what alternates the sign because of our even-odd rule with exponents. So I'd like to compare the graphs of f of x equals 1 over x and a sub n equals 1 over n. So here on the left, I have the graph of f of x equals 1 over x. We know these n's extend infinitely. And since we have that solid red line, we know there's a point here and here and here and here, like all the way, everywhere that there's a solid line, we have points. Well, a sub n equals 1 over n. Remember that the definition said that the domain is the set of positive integers. So we're starting with a sub 1 and going on. So I think I'm just going to list out some points. So a sub 1 is going to be 1 over 1 or 1. A sub 2, a half. A sub 3, a third. A sub 4, a fourth. So we're plotting the points, right? You're going to take the subscript. So 1, 1, 2, 1/2, 3, 1/3, 4, 1/4. Those are our points. Since the domain is only the positive integers, we don't connect these points. If we were to connect them, then we would be indicating that we had x values that were falling in between these integers, and that's just not the definition of a sequence. So you'll see that although the functions are kind of similar, the graphs are very different because our sequence only has positive integers as our domain. The graph of a sequence is a set of discrete points. And discrete points just means like separate real numbers, separate real ordered pairs. I want to look at one more type of formula that can define a sequence called a recursion formula. See, so far the formula is used for the nth term of a sequence, express the term as a function of n, the number of the term. Sequences can also be defined using recursion formula, and a recursion formula defines the nth term as a sequence as a function of the previous term. So it's going to tell us to do something based on whatever the previous answer was. Please note that when you're asked to list out terms of a sequence given a recursion formula, the first term has to be given. You have to be given a starting point. So looking at our recursion formula here, because we need to make sure that we can read it, a sub n is equal to 5 times a sub n minus 1 minus 3. This a sub n minus 1 right here, this is the previous term. You know, because if we're on term number n minus 1 would be the one right before it. So it's telling us to take the previous term, multiply it by 5, subtract 3. Well, the first term is given for us. Our second term, a sub 2, we take the previous term, multiply it by 5, and then subtract 3. So this is going to be 5 times 2 minus 3, which is 7. A sub 3, it's going to be 5 times the previous term, which is 7 minus 3. 35 minus 3 is 32. A sub 4, we're going to take the previous term, 5 times 32 minus 3, and that gives us 157. So here are the first 4 terms of our sequence defined by a recursion formula.